Hi everybody, it's Mrs. Mancuso, and today we are going to do what are called organic reactions. So I know that in the course of this year, we've learned some reaction types like synthesis, decomposition, single replacement, double replacement, but this time our reactions are all going to be organic. That means they're going to be involving these molecules that have carbon. And the reason why this is so important is you know that organic molecules, these ones with the carbons in them, make up all of our food, proteins, fats, lipids, nucleic acids, but they also make up things like our soaps, which is a huge industry. So maybe someday if you become a chemical engineer, these reactions will be really, really important to you. So for each reaction, I'm going to go through, teach you what the reaction type name is, how to notice it, what it looks like, and I'll try and do some review along the way too, so that we go back and we think about naming and all the things that we've learned about organic molecules so far. So the first reaction type is called addition, and when you think of addition, you think of taking two things and adding them together like a synthesis reaction, and that is what happens with addition. You have to start with an unsaturated molecule. So unsaturated means that it doesn't have all single bonds. It has to have either a double or a triple bond. And let's talk about where the hydrogens would be. I would have one here and here, like that. And the name of this, 3 carbons, so that's prop, a double bond, so that's ene. The double bond comes after the first carbon, so 1 propene. And since I know it's an alkene, I can figure out its formula. C3, H should just be double it, so 6. So I look at my molecule, 1, 2, 3, 4, 5, 6. Perfect. And now I'm going to add bromine to it. And I know bromine is a diatomic. It's in group 7. And when I add this to it, what happens, first of all, the double bond breaks. I'm going to keep all my hydrogens in their same places. And when I break that double bond, I can add one of the bromines here, because now I have a spot for that 4th bond. And I can add the other bromine here, and there's a spot for that bond. So it worked out perfectly. I started with adding 2 things together. I only have 1 product. When you have addition, you just have 1 product. It's one of the easy identifying features. And then to name this is a halide. And so I go to table R, and I would name this 1, 2, because I have a bromine coming off the first carbon and the second carbon. I have 2 of them, so I call it dibromo. And then 3 is prop, and it's now all single bonds, so propane. So I made 1, 2 dibromopropane. That would be my name. So that is what an addition reaction looks like. I'll just show you another one just to give you another example. Let's say I have C4H8 and I add chlorine to it. What I would end up with is C4H8Cl2. They would all come together. And my C4H8, let's say it looked like this. There it is. Its name would be 2, and then 4 carbons is bute. So butene, 2 because the double bond came after the second carbon. And I add chlorine to it, and it would look like this. 1, 2, 3, 4. I break the double bond and I add the chlorine here and a chlorine here. And then my H's would go around it. And so that is C4H8Cl2. And the name would be 2, 3 dichlorobutane. All right, so you get the idea. On to the next one. This one's called substitution. And so substitution, I'm going to switch. I am not adding together. I'm just going to switch one thing for another. So I'm going to switch a halogen for an H. All right, so I do not start with a double bond. I start with an alkane. All right, and so my alkane, let's do 1, 2, 3, 4, 5. And here's all my H's. So if I have 5, let's just review here. 5 is pent, all single bonds, so I have pentane. C5, alkanes have doublet plus 2, so double 5 plus 2 is 12. And I can check 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Perfect. And my halogen, let's add iodine this time. And so what can happen is you can swap or switch out one of your H's for an iodine. I'm going to draw all 5, 1, 2, 3, 4, 5 carbons, and I'm going to put it over here. I am randomly putting it in that spot. It's not like it had to go there. I'm just picking there. And I go ahead and I put the rest of these on, and I would have a second product, which again proves that it is not addition, because addition just gives me two reactants and 1 product. Here I have 2 reactants and 2 products. Now I took the H off, so the H is going to go with the other I, because over here, remember, I had 2 iodines, only 1 switched in. And then the name of this molecule that I drew, I would have to number from this side, because you always want to number from the shortest side. So this would be 2-iodo and then pentane. So the second carbon got the iodine, so that's what it would be. And HI would actually be hydroiodic acid. Now that we know how to name acids, we can name that one too. Hydroiodic acid. And if you're not sure, you go to table K where it lists the acids, and because it's a binary acid, which means it only has 2 parts, you put hydro in front of it, iodic for the iodine, and acid as a last name. All right, we are moving on to number 3. Number 3 is called combustion. And when you have a combustion reaction, you are burning something. So in our Zoom last week, we went over these reaction types, and someone said, oh, you burn propane in a grill. Could we start with propane? And absolutely we could. So prop means 3. So C3H, it's an ane, which tells me it's an alkane, which means I want to double it plus 2. So C3H8 would look like this. 1, 2, 3. There it is. And every time you do a combustion and you burn something, you need oxygen. You need oxygen to have a fire. So I'm going to add oxygen here. And then the 2 products are actually always the same. You always get carbon dioxide and water in a combustion reaction. So I want you to hold your hands up to your mouth right now and blow out. And when you blow out, you know that you're breathing out carbon dioxide air, but you also can feel water vapor on your fingers, and that is a reminder that your body is doing combustion. You're not burning propane, you're burning sugars, but as you burn those sugars, your mitochondria are what actually break down the glucose. They break every carbon from that glucose apart to give you carbon dioxide and water. And then you know I feel the need to balance this reaction. So 3 carbons means I'm going to have 3 carbon dioxides. And then 8 H's means I need to put a 4 here. And then here I have 4 and 6. So that's 10 oxygens. To get 10 oxygens on this side, I'd have to have a 5. So that's just that little chemist in me that loves to balance it out. I'm going to write another combustion reaction starting with glucose. C6H12O6, because glucose is what you eat and what you burn. So you know that if you hold your breath, you're going to do anaerobic respiration, which is like fermenting, which is not great. So I always want to have oxygen. It's an easy identifying factor, letting you know that that is a reactant and that it is combustion. I make carbon dioxide and water. I would need to balance this. I would need 6 of these and 12. So I would need 6 of these. And then this is 12. This is 6. That's 18. 6 of them are from here, 12 more from here. So this would be a 6. So that's all balanced out as well. All right, my next reaction type, my fourth one, is called fermentation. So fermentation is a type of anaerobic respiration, which means no oxygen gets used. We also know that fermenting is how you get alcohol. And in humans, it's how we get lactic acid, which can build up and cause your muscles to cramp. So all of these are identifying features of the reaction. You're going to not have any oxygen going in, and you're going to make an alcohol. Oh, and we know that an alcohol has an OH group on it. That's the functional group that we need. So let's start again with C6H12O6, which is our glucose. But we have the arrow and we have no oxygen there. Sometimes they actually put enzymes above here just to show that cells do this. And then instead of making carbon dioxide and water, you make carbon dioxide and an alcohol. The alcohol is usually ethanol. So let's see if we can take the word ethanol and show what it would look like. Eth means two carbons. Alcohol is OL, so that means I need to have an OH on it. I could have drawn it anywhere. I just chose to draw it there. So if I had to write the formula, this would be C2, H1, 2, 3, 4, 5, and then OH. That is my alcohol. And then I would also make carbon dioxide from this process. All right, so there is the alcohol that I made, and why don't we go ahead and balance this? So, whoops, if I have 6 C's here, I would have to make 3 of these, and I'm just going to do this out again so I have a little bit more room. C6H12O6 makes C2H5OH plus carbon dioxide. All right, so in order to balance it, I just like seeing it this way. And actually, I'm going to do it like this, and it'll be a little balancing practice for us. So carbons before and after, hydrogens before and after, oxygens before and after. All right, I have 6 before and I have 3 after. Hydrogens, I have 12 before, and here I have 5, 6 after. And oxygens, I have 6 before, and I have 1, 2, 3 after. All right, so if I want to double this, the easiest way is to double each of these. So this would be 4, 5, 6. Now my carbons are balanced. It also changed my hydrogen. So 2 times 5 is 10, plus 2 more is 12. So I've actually, in this process, already balanced my oxygens, or my hydrogens. Now let's check the oxygens. I have 2 here, and I have 2 times 2 is 4, so I have 6 here. Perfect. That was a good little balancing practice. All right, my next reaction type, so that was number 4. So number 5, saponification. Weird word, I know, but I want you to look at these 4 letters, and if you rearrange them, it spells soap. So saponification is making soap. The way you make soap, and so soap is just a really important chemical process, because if you think of how much soap you use on a daily basis, you wash your hands, you wash your hair, you use conditioner, shampoo, maybe use mousses and gels, you use bleach, you use laundry detergent, you use so many different cleaning products, maybe disinfectants for your counters and things like that. All of that is a massive industry. So the way that you make soap is you put a strong base and you put fats together, and that will make soaps. So these are usually just word problems when you see them in Regents chemistry, but again, it just is an important reaction because it makes soaps. All right, the next one, oh, I'm sorry. I keep doing that, screwing up the number. This is number 6, polymerization. So polymerization or polymerization is to make a polymer. So a polymer is a long repeating chain of monomers. So monomer is our individual unit, and when you put them all together, you get a polymer. So if you take glucose, C6H12O6, if you take glucose and put a lot of them together, you can get a starch. So a starch's formula would be C6H12O6 to the nth. N means like, oh, maybe there's like 1,000 of them all put together. So the most common way that you see a polymerization represented is you say N of this unit. This could be anything like that. And then they put it like this to the nth. So this is how many individual ones you have. So we call all the individuals monomers, and then you go together and you make one very large polymer. And the N shows the number that were connected. All right, the last one is actually my favorite one. This one is called esterification. And I guess I just really like it a lot because in college we made esters, and esters have this like fruity smell. And so we made one that smelled like juicy fruit gum, and we made one that smelled like bananas. And so esters are really cool chemicals. But I also love reviewing esterification because it's really good naming practice. So if I want to make an ester, I want to start off by showing my final product. An ester is going to have a chain of carbons. The carbon chain ends with a double bonded O connected to an O. And then after that is a branch. So to name this, my branch name comes first. So I have 2 carbons in my branch, and so 2 is ethyl. And then this is my chain. My chain has 3 carbons, so that's prop. And then again, you go to table R to help you with these namings. The naming end for an ester is anoate. So the name of this is ethyl propanoate. Ethyl because that is my branch, propanoate because that is my chain, and there's my functional group that I find on table R. Now, in order to make this, I have to put together an alcohol and an organic acid. So I know an alcohol ends with an OH because I can look that right up on table R. I know an organic acid ends with a carbon that has a double bonded O and an OH. So this part, I'm going to use red to show you. This part right here is going to be my organic acid. So in order to do this reaction here, I'm going to draw 1, 2, 3 with the double bonded O and the OH. And I'm going to name it. 3 carbons as an organic acid would be propanoic acid. And then to figure out the alcohol part, my alcohol part has the OH. That's over here. So I want 2 carbons and then an OH. And so 2 carbons is ethanol. And so in order to get ethyl propanoate, I would have to put together propanoic acid and ethanol, and those 2 together. So now I just want to really draw it out so that you guys can see how this happens. So here's propanoic acid. Here is my ethanol. I'm going to make the OH right here, just so that you can see it really clearly. And what I'm going to do to have this reaction, I'm going to take the H off of here and the OH off of here. And so one of the products is always water. My other product is I'm going to put the 3 C's, the double bonded O. The line is my connection for this bond that I'm making to the O to the 2 C's. And so that is my ester that I made. And again, this ester's name, you name the branch first. So the branch is what comes after the O. So that was ethyl propanoate. All right, let's do another one. I'm going to tell you what we put together, and you're going to figure out the ester that we make. So 1, 2, 3, 4 with a double bonded O and an OH. So this is my organic acid. And it has 4 carbons. So that means it's butanoic acid. And then the alcohol that I'm going to have is 1, 2, 3, 4, 5. And there's my OH. So this is 1 pentanol. And now I'm going to connect them. And when I connect them, I will make my ester. So again, this is where I want to connect them. So I take that off. So one of my products is going to be water. The other one is going to be, all right, I take the 1, 2, 3, 4 with the double bonded O. I connect the O and then I connect the carbons of the alcohol, which was 5. 1, 2, 3, 4, 5. Awesome. There's my ester. And now I need to name it. So you name the branch first. Here's my branch, pentyl. Branches always end in YL. I have 5 carbons, so that's how I got pentyl. And then this is my main chain. My main chain has 4, so that's but. And then the ending for an ester is anoate. So this is pentyl butanoate. So I think that after a while of doing this, it's pretty easy to go, this was my original alcohol. So I could just look at the ending. I could just look at the ester that I made and I could figure this out. My original alcohol had to be pentanol and my original organic acid had to come from this part of it. So it would have to be butanoic acid. So let's try that. I'm going to tell you that you made propyl heptanoate. And so in order to make propyl heptanoate and water, I always have to make water in this process, I know I need an alcohol, and the alcohol comes from the branch. So my alcohol was propanol. And then this part is where I get my organic acid. So heptanoic acid. And if you want to stay with me and draw it out, we'll draw what this would look like. So propanol would be 3 carbons with an OH, and heptanoic acid would be 1, 2, 3, 4, 5, 6, 7 with a double bonded O and an OH. And what I would make, I need some room because this is going to be huge. 1, 2, 3, 4, 5, 6, 7. Double bonded O, O. And then after it is my prop, so that's 1, 2, 3. And then to name it again, even though I already know the name of it, there's my branch, so that's propyl. And then there's my main chain, heptanoate. All right, that's it for organic reactions.